Hello everyone, Richard Walding here. In this video I'm going to give you some ideas about some ways you can modify one of the mandatory pracs from the Queensland Physics syllabus. I'll just get this started and you can have a look. Now, the mandatory prac was one to do with magnetic field strength and current basically, but I'm going to change it to measuring the force on a current carrying loop, and you'll see what I mean. Now, the original prac looks something like this. You'll notice it was just a pair of magnets with a wire going through it, and you changed the current through the wire, and you looked at the relationship. So that was force on a current carrying wire in a magnetic field, and that's the mandatory one for Queensland. Now, what we need to do is to think of a modification to that, and what I'm suggesting is this prac we're going to discuss now. Now, this prac, that page came out of my Oxford Physics book, page 408. Okay, I'm going to stop it there. This is the apparatus I'm going to use. Now, I just want to show you some of the bits and pieces. You'll notice there's a magnet, a little piece of wire there around a piece of wood, and there's a scale, electronic scale there. I'll just show you these bits and pieces. The wire that is in the diagram is this wire here. You might be able to see it's just 0.4 of a millimeter wire from J-car. It's called enamel wire, so 0.4 of a millimeter. It's fairly thin, and you can see it's enlarged on the screen. It's wound around a ruler. Now what I did, this is the little bit of ruler. All I did was take an ordinary old ruler, the meter ruler from school. Now I bought that from Office Works for $4, so you can cut it up, because it turns out it's a nice size to make a coil. Now all it is just a little piece of 10 centimeters from the end of the ruler. I cut a groove into the end. You'll be able to see there, little groove, and I just did 10 turns of wire. Now that's it on the screen. Also on the screen is that magnet. Now that's it here. I'm holding it up. It's just a rare earth magnet. Now I got that from Aussie Magnets, an Australian company. That was $13.20 each. I bought a pair of those, but I only needed one for this experiment. Plus there's about $13 postage. Now you can get them from a lot of other suppliers overseas for half that price, but I wanted in a hurry, so I did that. So they're the bits and pieces I'm using. Now I'll just continue on. I should go back and just explain the setup there. Now what I've got is the electronic balance. There's the scale pan there. I just printed off a bit of ruler, paper ruler, and that's off the internet. I just downloaded a paper ruler, and there's that piece of wood I was telling you about, and I did 10 turns of wire around that, and I've got a little piece of wire there sticking down as a pointer. There's my rare earth magnet on its side, and basically all I'm going to do is pass a current through this wire, keep it constant. I'm keeping it at 1 amp, 1.0 amps. Now I'm not showing that in the video, but that's what it'll be. Keeping the magnet the same, everything's the same. But what I'm going to do is move the coil, this loop here, or the coil, the 10-turn coil, away from the magnet. Now what's happening is there's an interaction between the magnetic field produced by the current carrying wire and the rare earth magnet, and you'll see in a minute that pushes down. It pushes down on the magnet, and you get an increased scale reading on the pan. At the same time, it's trying to push up on the coil. Okay, so that's basically the setup. Now the next diagram will show you that. Now it's just a little diagram. You've seen these before. There's the magnet on the pan. Here's the wire, the bottom of the loop. So basically that's just a part of the loop coming towards you. The dot indicates that it's coming out of the page. So the electric current is coming towards you. Now if you can see B from the magnet, the magnetic field B is there because it's the North Pole on that end, that side of the magnet. Now if you use one of your hand rules, now I teach the Fleming's left hand rule, and it's just a rule that will show you that there's a force on the wire upwards, which means there's a force, according to Newton's third law, force on the magnet downwards, increasing the scale reading. Okay, now you might use a palm rule. There's a couple of different rules to work out the forces on a current carrying wire. Now when I've got a distance d, the magnetic field is quite strong there because it's close to the magnet. As you get it further away, let's have a look at the wire, or the forces when the wire's way out here, 3 or 4 times the distance. That force, I've drawn it as a smaller arrow because it's a lot less, because the magnetic field is weaker there, and there's a formula relating all of that, which I'll show you later. Now here's the setup again. What you'll notice is, I'll just go back and show you that again. That's the loop of wire, the piece of ruler with the wire in it, and a little pointer I've just blue tacked on there. Here's the magnet on the pan. There's the scale reading there, it's in grams, so in this photo it's reading 1.64 grams. So that's my scale reading. And you can see the position here. I've got the pointer at 16 millimeters from the front surface of the magnet. Okay, let's move on. Now there's my ruler. It's just close up at the end. There's the top where I've got the terminals hooked onto the wire, and there it is. Now if you listened, you might have just heard that. I'll just go back a second. You'll hear, I'll stop it there for a second. Now you'll notice I've got no power going through the wire at the moment. Now I'm telling you that, you'll just have to take my word for it. There's no power going through the wire, so the scale reading has been tared, so I've made that 0. Now in a second you'll hear it click on, and then you'll so I've written the word power on, and then the scale reading will increase to 4 or 5 grams or whatever it is, and that's at a distance of 4 millimeters. You can see the wire is over the 4 millimeter mark. Okay, let's try. Now if you hear some birds chirping in the background, don't worry, it's a crested hawk, baby crested hawk that's fallen out of the tree, and its mother and father trying to teach it to fly, so they're signaling to it, but you'll hear that in the background. Here we go. You hear it, and there's the power on, and 6.32, so a distance of 4 millimeters, the scale reading was 6.24. Okay, we're at 6 millimeters now, and you've got the reading and so on. Now look, I'm going to go back and just show you that again. I'll just stop it there. I'll take it back to the start. The aim of this is for you to be able to collect the data here, so you can set up 2 columns, one with the distance in millimeters, and that's I'm doing it every 2 millimeters, starting at 4 millimeters. I can't get any closer. Starting at 4, and I'm going all the way up to about 40 millimeters in 2 millimeter increments. So the column for your distance is from 4, 6, 8, 10, 12, all the way up to about 40. Then you'll have 2 lots of scale readings. There'll be one for the first trial or first test, and then one for the second test, and you'll be able to record those. Now I'm going to stop talking so you can actually get those written down. Now you might wonder why I'm doing this if you can do it yourself. Now not all students have access to this equipment. I know it's fairly simple equipment, but you mightn't have access to it. You know, the American students, physics students, have been in their lockdown for a year now. They haven't had access to any of this stuff. And I've had some physics lecturers from the US using these videos because they can provide online data collection for their students. So this is a new one I've made up, and we'll see how it goes. So I'll just take it back to the 4 millimeters. Okay. Now all you have to do is wait till the reading settles down, and take the 4 millimeter reading, take the distance, and then the scale reading. Now I've made it as a video so you can scroll it back and forth. Now all you're looking for is a scale reading that's fairly stable. It's going to fluctuate a little bit, but we're only reading to 2 decimal places in grams, and it shouldn't vary too much. So here we go again. So power on, there's the birds, that's 4 millimeters, there's your first reading. Okay, we're up to 8 millimeters and so on. Now, if you're not interested in this part, you can skip ahead to the 4-minute mark, and that's when the second lot of data finishes. So I've done this twice so that you've got duplicates, and then you can work out uncertainty and percent uncertainty and do error bars and all stuff like that. Okay, so we'll just let this go. So that's 22 millimeters now, 24, about 0.8, 26.7, 28.59, and so on. Right, with 34.39, 36.35, and so on. Okay, and I think that might be the, oh no, 42 is 0.23. I've gone a bit further. 44, 46. Okay, now I'm going right back to get my second set of data. Now I'm just sliding I've got a retort stand, sliding that back to the beginning. It should read about the same as before, and I can't remember what it was, 6.48 I think. So this time it was 6 point something. Okay, 6 millimeters, 8, and so on. So I'll just let that go through till the end so you can collect your data. Now this is going to be a great modification. Now you're looking at a different variable, so it won't be a refinement, it won't be an extension. When you think about it, it's a redirection. You've got a different independent variable. You're changing the distance this time. Now this is different to the other prac where you've which was about the force between magnets. This is about a force between a magnet and a current carrying wire. So in my book I've called this, the original experiment for this 7.4, and this is a modification. And okay, so here's the data table. Now there's the distance in millimeters down the side there, 4, 6, 8 and 10 and so on, up to 44 or whatever it was, all to 1 decimal point. Now the headings along here, SR1 is the scale reading 1 in grams. So if you remember back, it was around about 6.26, so I've written that down. Yours might be a bit different if you're recording this yourself, but that's what I got, and then 4.84 and so on. Then I did a second trial, and that's scale reading 2 in grams as well. Now you'll notice the numbers aren't too far away from each other, but I'll come back to that in a minute. So there's the 2 rows, 2 columns of data you've got for your scale readings. Now the next thing to do is to convert the scale readings into a magnetic field strength B, because after all the prac is about the magnetic field strength varying with distance, not the scale reading. So I need to get a B value, that is the magnetic field strength. So if I just go on a little bit and I'll show you the formulas. Now what you'll see is this formula here. I'll stop it there. Now you're quite familiar with the formula F equals BIL sine theta. Now the loop was at right angles to the magnetic field. In other words, that piece of wood I had with the coil around it was parallel to the face of the magnet, and the magnetic field came out of the magnet at 90 degrees. So the theta value is 90 degrees with respect to the magnetic field. So sine of 90 is 1, so that reduces down to F equals BIL. So I've rearranged that. B equals F on IL. Now the force is just the basically the scale reading converted to a force in newtons. So what we do is just use F equals mg. So there's m, that's the mass of the, or the scale reading. Now that was in grams, so you have to convert to kilograms just by dividing by 1,000. So then you multiply by 9.8 to convert it to newtons. Then it's divide by IL. So there's the divide by sign. The I is 1.0 amps, and then the length. Now the length of the wire in the field, each turn of wire, that, in other words, the width of that ruler, this little ruler here, was 26.8 millimeters across. So that's 0.0268 meters. Okay, so I've converted the millimeters to meters there, but there's 10 lots of it. Okay, 10 turns. So you get all of that. So when I carry that, perform that calculation, I end up with converting 6.26 grams becomes 0.229 Tesla, capital T for Tesla. Then I've repeated it for the B2, in other words, for the SR2, the scale reading 2. And then I've done an average of those two numbers. The uncertainty is just max minus min on 2. So it doesn't really, it's the absolute value because it's the absolute uncertainty. In other words, you don't worry about pluses and minuses. So you just take these two numbers away. So on XL, I just took one from the other and divided by 2. Got that? Then I converted to a percent uncertainty, which is just the absolute uncertainty divided by the average B value, the average magnetic field strength, times 100. So there's my table. Now you'll end up with a table like that if you're doing this. The next thing to do is to plot the data. So you're plotting along the x-axis the independent variable, which is D in millimeters if you like, and then in the y-axis the dependent variable is the magnetic field strength. Okay, so that's these values here. Okay, so let's have a look at what we get when we plot that. I'm going to stop there straight away. Okay, so distance along the bottom, magnetic field up the side, and I get a beautiful curve there. You can see the dark blue curve. Now I've done let XL try to fit a power relationship to that, and it doesn't do it too badly. Little bit of a wobble there, but you can see the what XL is saying for the formula is y is equal to 3.0351 times x, which is the distance in millimeters, to the raised to the power of negative 1.5, pretty much 1.5. So in other words, the y value, the magnetic field strength, is equal to 3 times the distance in millimeters raised to the power of negative 1.5. Okay, another way you could say it is the magnetic field strength equals 3.0, etc., divided by the distance raised to the power of 1.5. Okay, it depends on how you wanted to say that. Okay, so let's move on. Okay, now the question is, and students always ask this, and teachers too, what should it be? Okay, now often people will say, oh, it should be an inverse square relationship because it's based around Coulomb's law. In the magnet, you've got circulating charge, and that produces a magnetic field. So it's a Coulomb law effect. But there's a real problem with this. Now, I'll show you here. When you take a magnet, don't forget, even though you've got a north pole, like I've got here, north pole, on the back is the south pole. So you might be getting some sort of downward force on the pan from the north pole, but just another 8 millimeters away is the south pole that's having a funny effect too. So it's not a single pole. You can't get a single pole as you can with, say, Newton's law for gravitation, where you can just have a body with mass, and that has an inverse square relationship in terms of gravity. Or you can have a single charge, like a positive or negative charge. With magnets, they always come in pairs. So you can't just have an isolated north pole. There's a South Pole somewhere around, and you have to take that into account. Okay, so in other words, there's no real set value for this, whether it's inverse square or inverse cubed or something. And what I've shown before, and there's a couple of videos I've made on that, it changes. It could be inverse to 1.5 for an early part up to say 10 millimeters, then change to inverse squared, inverse cubed, inverse to the power of 4. So it's not a constant value, and you'll see that in a minute. So but if you're writing this up as a student experiment, a modification, you could leave it there. You could say, look, it fits pretty well. Look at the lovely r squared 0.96. That shows that that formula fits the data pretty well. 0.96 is good. I mean, you'd like to get it high. You'd like to be up in the 0.99s, of course. And if that dotted line was closer to the real data all the way through, you'd be up around 0.99. Okay, let's have a look at the theory so we can work out what it might be. Now, if you were writing this up, you could stop there and just discuss all of the problems with the prac and some implications. You do all your data analysis and so on. If you want to take it a bit further, this is where it starts to get a bit tricky, where you're going to look at the theory behind it. At the moment, enough theory would be to say it could be inverse squared, because that seems to be a law of nature with gravitation and electric charge and so on. Okay, so this is where it's going to be a bit tricky. Now, I've got the magnet. Now, that magnet that I've shown you is basically north on the front side that I'm showing you now, but on the back would be the south. So this thing I've got on the screen, you can imagine it's only a single magnet, but think of it as the front half of the magnet is the North Pole, the back half is the South Pole. Now, the symbols we use, L is the length. Now, this one that I'm using, the one I got from Aussie Magnets, that's 40 millimeters across there. This is the width of the magnet, W. Now, you might think, well, that's not really the width, that's the height or something. But for the purposes of the way these magnets are sold, that's the width. Think of it as lying flat. That's the width. And then D is the depth of the magnet. Okay, now the width is 15 millimeters for this magnet I'm using here, and the depth is 8 millimeters. Now X is just the distance along the X-axis, so that'll be, you can use a ruler. Now I just stuck a ruler in here to show you what it would look like. Okay, so I just drew a ruler and put it in there. That's like that bit of paper I had on the balance. Okay, now the formula. Now, don't get too scared about this. This is a formula that physicists use. It takes into account the not only the North Pole, but takes into the South Pole, which is a bit further away. When you think about it, the North Pole is at the 0 mark, but the South Pole is only 8 millimeters away. So you can add on the depth here. So when you have an X value of, say, 20 millimeters, you've got a South Pole acting at X plus D millimeters away. Okay, so that's how this formula arose. Now, I've got the formula there, or the reference for that formula if you want to have a look. This is a German company that makes these magnets, and they've done a lot of investigation on it, and they've come up with the theory behind this. Okay, B is just the magnetic field strength. It's equal to a sort of a constant value that comes with the type of magnet you've got. Now, this is a particular type of magnet, so it has this reference value for surface surface magnetization. There's a pi there, arctans and so on. So you can stick all of that into a formula, And now I've done that. If you go to this site here, they'll provide you one that you could use. But I basically typed it all into Excel. Make sure these are in meters though, that's the only trick. But you'll work that out. And I've listed those things there. The reference value, now that's a N42 rare earth magnet. You look on the website. I had a look on the Aussie Magnets website, and this particular magnet, the 40 mil wide block magnet they call it, is said to be an N42, and that means something about the surface magnetization, and it's got a value, this constant or reference value 1.39. X is the distance in meters. Now X is a little bit more than just the distance d in meters. On the front of this magnet is a coating. Now it's nickel. There's a nickel coating on this. Now that nickel coating is 0.6 of a millimeter thick. Right now it's not very thick. It's as thick as roughly as thick as the wire that we used in the loop, but it's 0.6 of a millimeter is not very, or 0.65. So the X value is the distance from the wire to the surface of the magnet, but to get to the actual north pole of the magnet, it's another 0.65 millimeters or 0.00065 meters because of that nickel coating. And normally you wouldn't worry about that. It's pretty small. When we're talking about 50 millimeters in the distance, you're talking about 0.6 of a millimeter added on. But we know about it, so let's use it. Okay, now here's a graph. Now this is the theoretical graph. Now you'll notice I've tried to fit it with a power curve again, and you'll notice the theoretical graph is the heavy blue one, and it looks exactly the same as the graph I showed you from my real, the experimental data. Remember I said the dotted line was a little bit away from the line there, and it came underneath here. So it looks like my experimental values will match the theoretical values pretty well. Now the only way to show that would be and you can see by the coefficient up here, the exponent, x 1.465. I think the previous one was 1.49 or something like that. So it's very, very close. The r squared is about the same. I think the other one was 9.97. So the experimental value looks exceptionally close to the theoretical value. Okay, so that's great confirmation. So when I plot the two together, I'll plot my experimental data and the theoretical data. We'll see what we get. And look at that. Okay, so the experimental data is the orange, that's mine, and the theoretical is the one just underneath it. Now look how closely the experimental data matches with the theoretical value. It's beautiful. Now if you correlate the values, it's about 0.9997 or something correlation, but that doesn't mean they're equal. But in fact, as well as correlating almost 100%, they are almost equal in value as well. Okay, so there's you could apply some statistical tests to work out that they're the same. So basically we can say the theoretical and experimental are identical. If you look at the exponents, now those are the exponents of a power curve that Excel's fitting. That's these two blue and orange dotted lines. Okay, they don't fit the data perfectly, so we're not really interested in them. What I'm interested in is that the experimental and theoretical are so close. Now when you look at that, you have to be thrilled to see that. If you got that and you wrote that up, you could talk about that for ages. I mean, you've got a word limit, but think of how exciting that'd be. So that prac turns out to be absolutely magnificent modification. There's lots to talk about. You can use my data if you like, or why not carry it out yourself if you've got the equipment and see what you get. Okay, I'll just go on, and that's the end. I've got a number of these pracs written up. They're on YouTube, like this one, but there's a full list of the ones that are related to senior physics at that website, and you'll see it there for Unit 3 and 4, also for Unit 1 and 2. So that's that. Okay, that's the end of it. So thank you for that, and I'll sign out. Au revoir.